So now that we know how to draw free body diagrams, let's talk about how do I use those to solve force problems. Specifically first, forces that are balanced. So in this station activity, it could be a worksheet, but I think it's helpful to see it in person, so those in class got to do that. But you learn from home people, don't miss out. I took pictures. So for these stations, we're going to draw a free body diagram. Then all of these objects are at rest, which means forces are balanced. And what I mean by forces are balanced is the fact that any up forces are equal to down forces. And likewise, if I have any left forces, those together are equal to any right forces. So we need to know these relationships between up and down, left and right forces. And a new piece of information for this activity is I also need to know, how do I actually calculate gravitational force, or the force of gravity? Well, the force of gravity is also referred to as weight, and to find that, I do mass times the acceleration of gravity, where m is the mass in kilograms. It needs to be in kilograms, because it's a physics equation. And then g is this number we already know, 9.8 meters per second squared. So we'll be using this in some of our problems in this activity. So without further ado, let's look at station 1. You've got a mass attached to a spring scale, and it says determine the hidden tension, but you can also say let's determine the hidden spring force value. And so if I'm thinking about that, let's draw a free body diagram for this hanging mass. So I'm going to represent the hanging mass as a dot in my free body diagram. I know the mass has a force of gravity acting on it, pulling it down. And since it's at rest, it's not moving, I know there must be a force up as well. And that force up in this case is the spring force that the scale is registering. So if I am going to use this free body diagram to write an equation, I don't have any left or right forces, but I do have an up force, and that should be equal to any down forces we have, and the only one is force of gravity. So that extra piece of information I gave you about calculating force of gravity, this is where we need it. To determine what the spring force is, I need to know, how do I determine the force of gravity? Well, force of gravity is mass times the acceleration of gravity. So I need the mass in kilograms, and acceleration of gravity is 9.8. If I tell you the mass is 250 grams, what is that mass in kilograms? Well, if I convert, there's 1,000 grams per kilogram. That ends up being 0.25 kilograms, so I'll put that in for mass in my equation. So the spring force should just be 0.25 times 9.8, and if I plug that in my calculator real quick, you get a spring force of 2.45 newtons, which is correct. If you were in class, we would flip this card up, and on the spring scale, we would see a reading of somewhere around 2.45 newtons. Let's move on to a related problem, but now we're solving for something different. So, free body diagram, first and foremost. And as I'm doing these, I'm modeling the process we should use. We should not just be straight writing down numbers. Like, there are some numbers here, but I need to know what forces am I setting equal to each other before I start plugging in numbers, or else we're just going to get confused later. So this one also has two forces. It's pretty much the same problem. You've got gravity down, spring force up, and so spring force equals the force of gravity, because up equals down. Well, just like last time, and it's a good habit to get into, if you have force of gravity in your equation, go ahead and immediately rewrite that and replace it with mass times gravity. Because I know to calculate force of gravity, I take the mass and I multiply times 9.8. So the goal here is to determine the mass that's underneath this note card. Well, to determine mass, that means I'm looking for M. So I don't know M. G is 9.8. And then it tells me the scale reads 3.8 newtons. So that is a direct measurement of my spring force. So if I take 3.8, divide by 9.8, then I get a mass of 0.388 kilograms, which, if I convert, is a mass of 388 grams. And if I took this card off down here and I counted up the masses, this is exactly what should be there. Or in class, we've learned that this is not exactly correct because there's some guessing going on when I'm reading this scale value. So it should be somewhere close to the 388 grams. So now with number 3, looks like we upped the ante, and it looks way more complicated because now I've got 3 spring scales and a mass, and I'm looking for 2 different values. So first, before we even start trying to plug in numbers, again, just draw a free body diagram. I know this is on Earth, so it has a force of gravity acting on it, and I'm talking about the hanging mass here. There's a spring pulling up on this mass. There's a spring pulling right on this mass. And there's also a spring pulling left on this mass as well. So, in the very beginning, what does it mean for my forces to be balanced and this to be stationary? It means up force equals down force, and left force equals right force. Notice I did not put all 4 of those in the same equation. I can't do that. I have to think of my vertical forces and my horizontal forces separately. That's very important to remember. So in my force value 1, my hidden tension force or spring force is in the right direction, so I'm looking for this spring force on the right. How am I going to get that spring force? Well, let's look at my left spring force. That left spring force is 4 newtons. So by my equation, I know left should equal right. When I lift up this card here for tension 1, I should read 4 newtons on that scale. What about the hidden spring force value 2? Well, again, I wrote force of gravity, so immediately change that to mass times gravity, because that's how we calculate that force. So that spring force, when I open that card or lift it up, should be whatever the mass is times 9.8. But the mass has to be in kilograms. 420 grams is 0.42 kilograms. So I'll put that in for mass. G is 9.8. So 0.42 times 9.8. It gives me a force of 4.11 or 4.12 newtons. So when I flip that card up, this should be around what I read on that scale, a force of 4.12 newtons. So for this station, remember, we separated looking at up and down forces and left and right forces. Keep that in mind for station 6 when we come to that later. All right, so station 4. I've got a mass hanging underneath this cup. It is hanging from a spring scale, but it's also resting on a platform scale. So let's think about the forces acting on this mass. Well, I've got the weight of the mass, or the force of gravity. I've got a spring scale pulling up on this mass. And then since the mass is resting on this scale here, the scale is also pushing up with a force. What is that force called? That would be a normal force from the scale. So not only is the spring pulling up, but the platform is also pushing up on it as well. So how does that affect my up and down equation? Well, my up forces are spring force and normal force, so I add those together. Those two together should be equal to the force of gravity, or the weight of this mass, whatever it should be. Again, when I write force of gravity, I'm going to immediately rewrite this equation as mg instead of fg. So now the question, where does this 4.15 go? Well, that's the scale reading on my spring scale, so I'm going to put that in for spring force. This reading of 240 grams on my platform scale, well, this sort of gives me something about the normal force, but grams is not force. I gave this to people in class, but to change this to a normal force, this is going to give you a reading of 2.4 newtons. So instead of 240 grams, I'm going to put a force of 2.4 newtons. The goal here is to determine the hidden mass, so I'm looking for m, and I know g is 9.8. So if I add the left side together, I'm going to get 6.55 for my force total up, and that equals mass times gravity. So whatever 6.55 divided by 9.8 is, should be my mass, and that gives me a mass of 0.668 kilograms, which turns out to be 668 grams. So if I were to take this cup away and count up the mass by what it's labeled, it should be somewhere very close or very similar to 668 grams. Moving right along to Station 5. This is the exact same problem as Station 4, except I'm looking for the spring force now, and I'm given the mass. So if it's the exact same problem, we've got the exact same free body diagram. I've got the spring scale pulling up. The platform scale is also pushing up at the same time. So my total up force is that spring plus the platform scale. And I've got weight or force of gravity pulling down. But again, whenever I write force of gravity, immediately write it again as mg. So let's start finding numbers here. I'm looking for the spring force, so I'll leave that be. I again gave this to you in grams, but to convert that to a normal force, I'll go ahead and tell you that's 2.75 newtons. So I'll put that in for the normal force. The mass is 450, but to put mass in for my force of gravity, I need it in kilograms, so that is 0.45 kilograms. So I'll write that there, and then g is 9.8. So if I multiply the 0.45 times 9.8, we get 4.41. So if I solve for spring force here, it's 4.41 minus 2.75, and you should get a spring force of somewhere around 1.66 newtons. That's what I would read if I flip this card up and I read the scale, somewhere very close to 1.66 newtons. All right, now we get to Station 6. This one looks a bit different because I don't have a hanging mass. What's happening here is I've got a spring scale pulling on this wood block, but nothing's moving. I want to determine the force of friction on the wood block. So on the wood block, it kind of gives me a hint that my free body diagram is going to be of the block itself. So focus on the block here and the forces on the block. Well, the block itself has a weight, and yes, like this black mass contributes to that weight, but I just have the black mass on the block to keep it still. So we can include that in this force of gravity. The counter has to push up to counteract that with a normal force. I clearly see that the spring is pulling this block to the left. Well, why doesn't the block move if it's being pulled to the left? That must mean there's some force to the right stopping it from moving. What is that force that is stopping this block from sliding? That would be our friction force. So, up forces and down forces. Well, up is normal force, down is gravity, the force of gravity. Again, I'll immediately rewrite this as normal force equals mg. So this relates my vertical forces. But that's not what I'm looking for. I'm looking for the force of friction on the block. Let's look at my left and right forces. Left is spring force, right is friction. So I'm looking for the force of friction. How am I going to figure out the spring force? Well, this tells me this scale reads 3.5 newtons. That's telling me the force that is felt in the spring. So spring force is 3.5 newtons. That is the force of friction. How do I know that? Because I've come up with this equation. How did I get that equation? Because I drew my diagram. So these steps are very important to follow. It may seem pretty elementary now when we don't have very many forces, or I'm just setting left equal to right, but I'm telling you, first, draw the diagram. Second, write your equations. And then once you've written your equations, then we can start putting numbers in. That's going to be a good habit to build now as we go through the rest of the semester with force problems. If I'm doing it in these steps, free body diagram, equations, then plug numbers in, it's going to make problems a lot simpler down the road once we start adding in some more complexities. But we have one more station before we're done with this video. So, station 7. I've got a hanging mass here, so I want to draw a free body diagram for that hanging mass. The mass on the hook has a weight, Fg. I see there's a spring holding it up. But then what am I looking for? I'm determining the tension force in the string, which we may notice is right here. There's a string pulling down on this mass. So there's an extra tension force pulling down. What does my equation look like now for this free body diagram? Well, up forces equal down forces, but I have two down forces, so I'll add those together. Again, I'll rewrite this equation, replacing force of gravity with mg, because that's just what we should do. Now, where can I find numbers? The scale reading 4.1, that's directly pointing towards the spring scale. That is my spring force. A mass of 150 grams converts to 0.15 kilograms, so I'm going to put that in for the mass here. I know G is 9.8, so that means what I'm looking for is the tension, which is the question. Determine the tension force in the string. So to do that, let me first multiply the mass times 9.8, 0.15 times 9.8. I get 1.47. So to solve for tension, I subtract the 1.47 over. And for this particular problem, we get 2.63 newtons. Now, there's no way to really measure that, but just know that the weight of this and the tension together should equal what this force is. So, mathematically, this is correct. I could put a spring scale or a force sensor on this string down here, and we could measure that, but we didn't have that in this problem. But this would be the tension if the spring force is 4.1 newtons and the force of gravity on the mass is 1.47 newtons. So hopefully this video was helpful. Again, follow the process. Free body diagram, write your equation, or equations if there's multiple, and then start plugging in numbers to try to solve for something. If you watch this video, half the quiz tomorrow you'll be golden on, because it is just these problems again. I just changed the numbers.